Okay, this is Introduction to Environmental Engineering and the topic one, the first topic in this course, Introduction and Mass Balance. We'll discuss some of the definition and other things like that, then finally the mass balance. So these are the topic one overview. It covers mainly the course learning objective number 1.1. So that says interpret the federal, state environmental regulations and standards and solve engineering problems using mass balance. Not the energy equation, mass balance equations. Okay. So this part and the second topic we'll see the energy equation part of it. So these are the outline that we are thinking to cover into this topic. First one is the definition of engineering and civil and environmental engineering overall. Then codes of ethics. We'll discuss a little bit of ethics, codes of ethics, engineering ethics or environmental ethics. Then environmental systems overview. We'll do three different systems: water resource management system, air resource management system, and solid waste management system. Then we'll see a little bit of environmental legislation and regulation, water quality management, regulation related to this, air quality management, solid waste management, and hazardous waste management. Environmental ethics, importance of lifelong learning, these are the one we'll see. Then we'll start the mass balance, unifying theories, conservation of matter, conservation of energy, conservation of matter and energy, materials balance, fundamental approach to problem solving, time as a factor. These are the one we'll see. Okay, so here are the learning outcomes for this topic. So student should be able to define engineering and environmental engineering, identify environmental engineering system and subsystems, interpret the federal and state local government regulations, water quality management, air quality management, solid waste and hazardous waste management, discuss the code of ethics and environmental ethics, and recall the mass balance equations and solve engineering problems using mass balance equations. So here is the definition of engineering. So it's a profession in which knowledge of the mathematical and the natural science gained by study, experience, and practice is applied with judgment to develop, to develop, utilize, and economically be the material and forces of nature for the benefit of mankind. So okay, so whenever you say benefit mankind means that's the main thing, right? Everything we do, so in our cases we use the judgment economically for materials and the forces of the nature that for the benefit of the mankind. So in this case we can say scientists discover things, engineers make them work. So for example, if I can give you an example, Newton is F equal to ma, Newton's second law, right? F equal to ma. So we have used this equation several times in fluid mechanics to develop different equations, right? Even P equal to gamma H, we try to use that one too. The other cases that we used is the fundamental equation of, so impulse momentum equation, right? We use F equal to ma. So that's what it means. The scientists discovered things, but engineers used it to make something work for our human being and other things like that. So what is environmental engineering? So ASC definition, first one is the provision of potable, safe to drink, palatable, pleasant to drink, and ample public water supplies. We have to make a provision for that. So that deals with the environmental engineers. So this is number one. And number two is proper disposal of or recycling of waste and wastewater. Okay, number three, control of water, soil, and atmospheric pollution. Finally, noise pollution is also another one. Okay, there are three parts of the definition that is done by ASCE. Since the environmental engineering is the first course, in this case, introduction to engineering, these are very important to understand and know that. Okay, what is environmental engineering? If we continue it, environmental engineering has developed from the historical branch of civil engineering known as sanitary engineering, involving drinking water and wastewater treatment initially start with. So the rapid growth in 70s and 80s, this truly interdisciplinary field involves the application of scientific and engineering principles to improve the maintain the environment for the protection of human health, for the protection of nature's beneficial ecosystem, biodiversity, environment related enhancement of quality of human life. So that started with. So through education and experience, environmental engineers develop understanding of the Earth's biological, chemical, physical, and geological system. They use this information to develop engineering plans to design solution of environmental problems caused by pollution. So they are also being increasingly called upon to develop pollution prevention plans to keep environmental problems from occurring in the first place. That means a prevention, mainly prevention issues here. So environmental engineers often work with civil engineers as consultant projects, but may work with engineers and scientists from all disciplines, maybe biologists too, as well as government regulators, official, private municipal agencies, industrial and public interest groups. So all of those are part of the environmental engineering work. So fundamental principles, ASC Code of Ethics. So it says the engineers should uphold and advance the integrity, honor, and dignity of engineering profession by using their knowledge and skill in the enhancement of human welfare, being honest and impartial, and serving with fidelity the public, their employers, and clients, striving to increase the competence of prestige and engineering profession, support the professional and technical societies of their discipline, like we become ASC member and other things like ACA member. So that's how we support all of those. Okay, the fundamental canons. Fundamental canons are shall hold paramount the safety, welfare of the public in the performance of their professional duties. Engineers shall perform services only the areas of their competence. Like I'm a civil engineer, I should not serve in electrical engineering areas, or even if I'm environmental, I should not do structural design. So things like that. Engineers shall issue public statements only in an objective and truthful manner. Engineers shall act in professional matters for each employer or client as faithful agents of trustees and shall avoid conflicts of interest. So that's very important. Then engineers shall build their professional reputation on the merit of their services and shall not compete unfairly with others. Engineers shall act in such a manner as to uphold, enhance the honor, integrity, and dignity of the engineering profession. And engineers shall continue their professional development throughout their careers and so on. It's a kind of lifelong learning. Then the next one is the environmental systems overview. There are three systems that we mentioned before. So these are like water resource, air resource, and the solid waste, right? These are the three that we discussed. So they have some water resource system has some kind of two subsystem, is water supply system, subsystem, other one is wastewater disposal subsystem. Water supply is mainly the nature of the water sources determines the planning, design, operation of collection and purification, transmission, distribution works. There are two major sources. We'll discuss more of those source, surface water, groundwater in the next topic, topic 2. So the two sources are major. These are surface water supply major. Other one is the groundwater. Okay. Reasons for estimating average daily water consumption if we do certain things like that. So here is the reason: to determine the ability of a water source to meet continuing demands over a critical period when surface flows are low and the groundwater lowest elevation. Then we have to determine that for the purpose of estimating quantities of stored water that would satisfy demand during the critical period. So that's the reason we have to do that. This graph shows, like, so this is the average. In the morning, we don't have enough. This is the supply we are doing. This is the looks like hour. This is the shortage. This is the hour. This is the shortage. This is the hour. So that means this how it does work. So okay, so in this case, if we have any overhead storage tank, I don't think I have the picture here. I might have it later on, but anyway, so if I am here and I have an overhead storage tank here, okay, so for example, this is my overhead storage tank, okay. So then when I'm here, I'm putting the water back into here. When I'm here, I'm putting the water back into here. When I'm the water, I'm putting the back into here. When I'm here, I'm bringing the water from here to here. Okay, I'm bringing the water here. So that's how we can balance and we can keep up with the average flow, that means pumping rate and other things like that. So peak demand rates must be estimated in order to determine the plumbing and the pipe sizing, pressure losses, and storage requirement necessary to supply sufficient water during periods of peak demand. So that's the idea of that. So here are factors influence the water consumption, industrial activity, meterage, system management, standard of living, climate. These are the major factors. We have some minor factors: extent of sewage system, system pressure, water price, and availability of private wells. So these are the one. So this table shows a little bit of water usage in different time of the country in the USA. So 2005 was 371, 2008 580, 99 440, 1970 was 6. Why it is going down? So it is going down because of, with the time, because of the losses. We are reducing the losses and we are increasing the efficiency and other things. So maximum daily can be calculated using 2.2 times the daily average and peak hourly 5.3 times daily average. So that's how we calculate, because of, you guys in the picture, right? So here are some of the other countries that shows some part of it. Australia looks like 1,400 liter per capita per day. So liter, the 1 gallon equal to 3.785 liter, right? So Canada 430, China looks like Nigeria is only 25, meaning in this case, the underdeveloped country, they don't have that much of requirement anyway. I mean, they cannot afford it. So now here is the domestic water usage in gallons per day per person and person population growth from 2000 to 2015 in the USA. Okay, so this is the domestic water usage gallon per day. So certain areas, right? So if I say this area means this two, right? This two has a 151 to what is it, 200. Then if I go here, looks like these are may not be that like high uh, rich city and other, I mean the state, 0 to 75. So average in this case it comes out to be 440 liter per capita per day in 99 data. You can say 450 and so on. Okay, so so this is another usage variation. Looks like these are the usage. Toilet is 24%, shower 20%, faucet 19, clothes washer this leak 12, and others 8%, because others cannot be fall into this. Seasonal variation, daily variation, and hourly variation of this. This is daily, this is day of the year, and things like that. With the time is showing the variation. I showed you the picture before. Very similar, but it shows different. So this is kind of average. This is kind of average. Okay, so this is the picture I wanted to show you. Looks like I draw a little bit in there, but here is the most daily water usage variation in the demand. This part goes to the tank. This part goes to the tank, whereas we bring this whenever we need to be here, need to be here. So things like that. Okay, wastewater disposal system. The safe disposal of human waste and wastewater is necessary to protect the health of the individual, the family, and the community. To accomplish satisfactory results, human waste must be disposed of so that they will not contaminate any drinking water system. They will not give rise to the public health hazard by any being accessible to insect, rodents, and other things. They will not give rise to the public health hazards by being accessible to the children, and so on, right? So they will not cause violation of laws and regulations. They will not pollute the contaminated waters or contaminate the waters, bathing, beach, shellfish, and other things like that. They will not give rise to the nuisance due to the odor and unsightly parameters. So these are the main objective of these things, wastewater disposal system. Okay, here is the wastewater management system. Shows a flow chart basically. This is the source where it's coming from. Then it goes on-site processing, means septic tank, where the connection is not there, sewer line connection is not there. So, or if we don't have a septic tank, and then directly from here it goes to the wastewater collection system. Then from transmission and pumping, if we have it, if we don't have it, can go directly to the treatment plant if it is gravity. Then finally treatment is done, then goes to the disposal or reuse, final disposal or reuse. So this is called wastewater treatment plant, or PWT, POTW, public works treatment, publicly owned treatment works. And this is wastewater treatment plant. Okay, air resource management system, the balance of the cost of benefit obtained result quality is termed as the air resource management. The air resource management programs instituted for two most defensible reasons. Air quality has deteriorated and is a need for correction, and the potential for a future problem is very strong. So in order to carry out an air resource management program effectively, all the elements shown in the figure must be employed. So the figure there, I think there is a figure in their book, figure 1.5, page 15. You can take a look. It's a big flow chart that shows everything. Okay, we are going to stop here.